Hello, everyone. Welcome to the seminar this week. The speaker today is Massimo Vergassola, who comes from ENS, recently came back from the US. He's a physicist. He's going to talk about biological behavior. He works on a variety of topics, but narrowed it down so that he can speak in less than 4 hours. Please feel free to interrupt, right? Okay.
Yes.
So don't wait until the end. Yeah.
Thanks. Thanks, Agnese, for the invitation. Thanks, everyone, for being here. What I'll tell you today, as Agnese said, we are physicists, but we thought a few years ago that it would be useful and interesting and instructive, and it would bring good fruits to apply methods from machine learning to animal behavior, which is our main interest. So I'll tell you today, we cover different topics. One of them being the olfactory searches by insects or rodents, which is something that we are doing. It's the reason why I'm here to finish some work with Agnese. I won't tell you about this, maybe for next time. And what I plan on doing for today is mostly to tell you about soaring flight, which is some work that I've been doing while I was at UCSD. And then some more recent work that we've done purely theory, we've done during the lockdown, as we couldn't do any experiments, so we decided to get some theory done on olfactory trail tracking by the end of it. So that's the plan, mostly to do this, and then to get by the end to tell you a few things about this. And as Agnese said, feel free to interrupt anytime. It's going to be much more fun for you and hopefully, and certainly for me. This is it's work that I've done over the years. So these are the different people I've been working, the project on olfactory searches I started before leaving to the US when I was at Pasteur. Then most of what I'll tell you today was done while at UCSD. You will see that the experiments were done in the desert for good reason. And it was mostly funded by the Simons Foundation. And these are the people, you will recognize the names as I go through over the work. Okay, so let's get started on soaring flight, and let me show you what soaring flight is. The best way is to show you a movie. It's a very nice movie which was taken in this paper of 2008 by Wiksek and collaborators. And what you will see is the GPS trace of the flight of a falcon. Okay? And here it is. It's flying over an open land. And at a certain point, it starts to spiral. What is happening at that location of the spiral is that the bird has picked up an ascending current, and it's circling this ascending current. So you can imagine in the zeroth approximation this kind of a tube, and it's spiraling around this tube, and it's going up. And it's using this ascending current to gain height. In the case of the falcon, this is to gain a view over the land in such a way that he can predate. In fact, in addition to the falcons, there are other ways this kind of strategy of flight is used, in particular by migratory birds. There's a nice book by Jan Newton that you can look at. And if you look at these migratory routes, they're very dense on thermals. These thermals are these ascending currents that are getting produced. I'll explain in a couple of slides how they get formed. Actually, I won't tell you much, but just the basic physical principle. And these migratory birds, they use these ascending currents in order to again, they don't flap the wings. Flapping the wings is much more costly metabolically, as I'll explain in the next slide. And therefore, they use these ascending currents to do soaring flight, which I will explain. And you can get the principle of this. This is some recent work in science. It's also used by marine birds. These are frigate birds. And you can see the way they're using this soaring flight. This is the height as a function of time. the thermals are being produced at this location, and you can see that these frigate birds, they can get at height which can be of the order of a couple of kilometers, and then from this couple of kilometers they fly down without flapping their wings, and this way they save energy. Yes, is the height along the trajectory. The color of what? Oh, this one is the height. This one is the height. So what is, can I? Sure. So this is just flying. Now it's going to pick up the spirals, and the spiral corresponds to this face here. So it's going up. So while spiraling, it's gaining height. Same thing here. It's starting down here, then it's picking up a thermal, it's going up, it's reaching here, and then it's flying down by gliding. And I'll explain more, you will see the plot. Now, one point I'd like to make here is that you shouldn't think of these thermals as elevators that they take, because the ascending currents that they have, they're being produced by turbulence. So they are very noisy, they're very fluctuating. As you can also tell from this plot here, it is very tilted, which means that the wind, in fact, is tilting the ascending current. So you have to follow this ascending current. And within the ascending current, it's not like you're going up at each and every location, because by basic principle of fluid dynamics, if you have some mass of air which is going up, there must be some descending current which somewhere, and therefore you have to be careful in not picking up the downdraft and in picking up the updraft. So navigating into this thermal, which will be the whole difficulty of the problem, is not an easy task. Don't imagine this that sometimes is getting plotted in some books. It's much more complicated. Okay, so let's get some energetics. Why is this important for the birds? And the idea is very simple. The idea is to write down the balance of energy. You take U is the velocity of the bird with respect to the ground, V is the velocity of the air, and W is the wind velocity. So clearly the velocity of the bird with respect to the ground is the sum of the velocity with respect to the air and then the velocity of the air. That's the sum. And now you write down the energy with respect to the air, and you take the derivative, and you get an expression which is up there. You can look at the details in this paper here. Now, if the bird is flapping, okay, you have some thrust, T, and D is the drag. Okay? So fluid dynamics, you flap the wings, you're going to generate some thrust, and there's some drag which is given as in standard fluid dynamics book by this expression. Is just dimensional analysis, where CD is the coefficient of drag. Now, if the bird is flapping and it's keeping a constant velocity, then the drag and the thrust, they balance. But this is not very useful because the bird is going to consume quite some energy. Now, the advantage for the bird is not to flap their wings, so the thrust is equal to 0. If the thrust is equal to 0, then it means that the drag, which is always present, must be compensated by the other two terms. So there's two possibilities. One possibility is that there's ascending velocity, Wz is not equal to 0. Or the other possibility is that the last term over there, V dw dt, is compensating for the drag which is over there. That's a case which is called dynamic soaring. I'll show you momentarily what it is. It won't be important for today. The case which of interest is that if you have Wz which is non-zero, so you have some air which is going up, of course you can exploit this in order to go up. Now, you can estimate how much you can save by doing this And the cost of migrating over distances of the order of 1,000 kilometers, which are typical distances that you've seen in the previous slide, is something of the order of 5,000 kilocalories if you put some numbers, the typical numbers that you have here. Now, 5,000 kilocalories, it's about 500 grams of fat, which is one quart of the total mass of a typical bird, over the whole distance of 1,000 kilometers. Flapping at this typical velocity here. Okay, so the typical velocity is 15 meters per second, which is the speed they have. The mass is estimating. These are ballpark estimates. It's just to give you a sense that without doing this kind of soaring flight, that's the amount that the bird should consume. And 1/4 is like for us, you can just estimate running with 1/4 more of your weight or without this weight. It's something which is quite substantial. And this is to explain why this soaring flight is important for the birds. Now, this is the last term. This is just to tell you that this was not invented in the last year. This is not the first work on soaring. It is something, in fact, that was already thought by Lord Rayleigh in '83, the famous fluid dynamicist. But he was more than thermal flight. He was more interested in the last term over there. And he concluded, it's a Nature paper of 1883, he concluded that if you have no thrust, then these three terms, and you're flying at a constant velocity, then there's no other choice. E dot equal to 0 is telling you that either the course is not horizontal, which is WZ non-zero, either the wind is not horizontal, which is the last term, and the wind is not uniform, which is make the last term non-zero. Now, he was more interested in the case 3, that's called dynamic soaring. And another bit of history that I want to show you is that Leonardo didn't explain all these phenomena, but he observed them probably while he was in Rome from the top of the hill in the Vatican. That's a very good place for observing a soaring bird. And you can see this soaring flight, this spiral that you've seen before, then the bird which is gliding in here, and then it's picking up a spiral again. And this is the phenomenon of dynamic soaring, is riding as usual in the mirror. And then this is the phenomenon of dynamic soaring, which is that you have to descend when the wind, and then you have to go up opposing the wind, which is the phenomenon of dynamic soaring that Lord Rayleigh was observing, and I won't discuss this today. So that is so much for the history. What are thermals? I won't give you a course on geophysical fluid dynamics. I think that would take too long and it wouldn't be the point. The basic principle is very simple though. You have some heating on the ground. The ground is getting heated up, for example, by the sun. And therefore, it's warming up. The air which is close to the ground is getting heated up with respect to the air at higher levels. And therefore, it starts raising. It's creating for the aficionado some baroclinic effects, which are generated in vorticity. So this generates a loop like this, which makes the air go up and then recirculate and go down. And it's creating the effect that you can see in these plots. This is the height, and this is the hour of the day. And the color code is measured by LiDAR, which is laser technique to measure the velocity of the air. You can see the color code is that red is a substantial vertical velocity. So you can see that in the hot hours of the day, you have some ascending currents, which are here, that last, as you can tell, for a few minutes, and then they disappear. But it's quite substantial. You can have several meters per second of ascending velocity, which is going up. And this is what the birds are picking up in order to go up. So how this is getting used by the birds is not specific to the birds. It's also getting used by flying vehicles of humans, which have a range of applications that can go from surveillance. It can go, of course, for military applications, but there's also plenty of applications that have to do with civilians application, like for archaeology, like for the surveillance, like for the environmental controls. And the way this is getting used is very similar to what the birds do. So you pick up an ascending current over there, and then you glide. These autonomous flying vehicles, as the name says, autonomous, they fly without any human being, and they can fly without engines. So the real bottleneck in these applications is that usually the battery is relatively short-lived, and therefore it's very convenient to have an alternative source of energy, like the thermals in this case, that allow the flying vehicles to stay aloft for much longer times. So that solves the problem, can solve or at least alleviate the problem of the energy source. And I'll tell you, as I was saying, there's different forms of getting energy, of extracting energy. There's another form of getting energy, which is, however, not particularly useful to go somewhere, but you can have a lot of fun, as you can see here. This is La Jolla on the Pacific coast. And what happens is that there's wind which is blowing from offshore, and it's hitting the mountain which is here, the cliff which is here. And what happens when you have wind blowing this way and hitting a cliff is that the streamlines of the flow, they get compressed at this location. And therefore, you might remember from Bernoulli law that if you compress the streamlines, this is going to produce some pressure. And this pressure is going to produce the lift, which is here. And the aircraft is going to get pulled up. Okay? From this case, you can see where the danger of all these flights lies, because if by any chance you manage not to stay on this side, but you happen by mistake to go on the other side, you have the opposite effect, which means that the streamlines, they're going to open up, and you're going to get the downdraft. And that's the reason why, typically, every 2 or 3 years, in La Jolla, you have someone dying doing this kind of glider flight. So it's not a simple problem to fly. In this case, it's kind of relatively easy to figure out because you have the cliff, which is giving you an idea. In the case of a thermal, you don't know exactly where the downdraft is, where the updraft is. So you have to figure it out based on the mechanical cues that you receive. Okay, so as I was saying, the difficulty is that these flows are turbulent, they are highly fluctuating, and we are interested in animal behavior. Therefore, the questions that we would like to, most of the works that have been done so far, they are purely observational. So you observe the bird doing this kind of non-trivial behavior, but there's no real understanding. So we decided to embark on all this. And try to answer a few questions like what exactly the bird is sensing. Is it vertical velocity, temperature, gradients of vertical velocity? And once you know what quantities the bird is sensing, how should they use them? Okay? So imagine I give you a trace of, let's say, what's the vertical velocity? How should I respond to the previous history? And this gets to be a problem of devising a policy of action. So this starts to be framed in the language of machine learning. You have some stimuli, you have a history of stimuli, and you would like to know what kind of action I should take in response to this history of stimuli. The problem in doing this with birds immediately is that there's no data. It's very hard to monitor immediately from the birds. There's lack of data. So we decided to turn the problem upside down and to say, okay, let's forget for a second, we'll get back to the birds at due moment, but let's start with the problem of how an agent, flying agent, like for example, the autonomous flying vehicles that you've seen before, what should such an agent do? And in particular, what sensorimotor cues would be useful for the task, and how these sensorimotor cues should be used in order to gain height. Okay? So that's, we turn the problem, and then possibly we'll get back to the birds. Okay? Now, as you all know, I don't need to tell you that in order to train a system, it takes quite a number of realizations, and it's not obvious that in the field you can have enough data. So we decided to take even one more step in the simplification, and to say, rather than doing the experiments immediately with the gliders, let's do some numerical simulations, and let's see first what happens in numerical simulations. Also because it was not obvious. It was one of the first applications in machine learning applied to turbulent flows. So it was not quite clear how the training and all the machinery of reinforcement learning would cope with the existence of long correlations in a turbulent flow. So we decided to look at numerical simulations. And the difficulty of numerical simulations of the atmospheric boundary layer, so doing a realistic simulations of what happens out there, it's quite complicated. It's quite complicated because you have to cover, as you've seen, distances of the order of kilometers in the vertical height, at least a couple of kilometers you have to take. These birds are flying over distances of kilometers on the horizontal, on the two directions. So you have kilometers, kilometers, kilometers. And you want to resolve decisions of changing direction of flight, which are taken over timescales of the order of seconds. They are flying at meters per second. Therefore, what you want to do is that you would like to resolve distances of the order of meters in boxes which are several kilometers cubed. Okay? So that's something that even with the computers nowadays, it's not possible to do. What you have to do is that you have to, in these simulations which are done at Argonne lab of the atmospheric boundary layer, they can resolve order of 50, 100 meters, not meters. Therefore, simulating directly the atmospheric boundary layer is not possible. And therefore, we took one step down and we decided to simulate something which is not exactly the atmospheric boundary layer, but it has the same flavor. So this way we can develop the machinery, we can develop the methodology, and then we can go back to the real situation. And some of you might be familiar. The example of fluid dynamics which we took is the example of the so-called convection. So it's the boiling pot that you have when you warm up for pasta. You warm up the bottom and you cool down the upper part. And because of the same effect that I told you before, the water or the air which is close to here, it's going to raise and it's going to cool down as it gets here, and it's going to generate these ascending and descending currents that you see here. This is the temperature, the plot of the temperature, and this is the plot of the velocity. Now, there's some equations which are the fluid dynamics equation. U is the velocity, and there's a few numbers. This is the Boussinesq force, which is the due to the convective effects. And then this is the temperature which is obeying, which is getting transported by the velocity, and this is the diffusion that you have here. So these are some equations that you can integrate numerically. You can simulate, and you can get this kind of plots. And of course, it's much easier now to imagine what you can do, because numerically simulating this is much better control, and you have an ensemble of flows where you can train your agent and find out what is good and how it can possibly fly. Now, This is the first step. Now, the second step is that you want to have an agent which is that you want to put and you want to find out how they should fly. So the second step that you need to do is what is the aerodynamics of a flying gliding object. And this has nothing to do particularly with birds. Any flying vehicles, bird or whatever it flies, obeys the laws of aerodynamics, which are relatively well established. And in particular, there's one object which is the essence of how it flies, which is called the glide polar, the polar curve. The polar curve, what it tells you is that imagine you're flying a certain number of meters in the horizontal. Imagine you want to fly on the horizontal, let's say 10 meters, and you're not flapping the wings. Okay. Now, this energy of flying 10 meters in the horizontal must come, because there's energy conservation, it must come from the only source of energy that you have, which is the potential energy of being high. So if you want to fly 10 meters horizontal, you have to lose some height. And that's how you convert height into kinetic energy. So potential energy is getting converted into potential energy. And of course, there's some drag, so you lose some energy. The polar curve, which is the parabola which is up there, is telling you for the sync rate, how it gets converted into horizontal speed. And there's an optimal, the best glide angle is the one where the intercept is, the angle is as small as possible, because you gain as many meters horizontally per given vertical. Just to give you some numbers, these are the glide to sync ratio of some little birds. And then this is the frigate bird that you were seeing in the first slide. And these are some modern sailplanes. They can make 40 meters for a meter of height loss. So it's pretty impressive what the modern sailplanes can do. The essence of the flight is given by the polar curve, which is up there. And if you look at what the birds do, of course, they change a little bit. These polar curves, they're not exactly all identical. It couldn't be, because these birds, they have different characteristics. But they all look like a little bit like this parabolic shape that you have over there. And therefore, what we took was a typical curve, one of those. And we simulated the flying agent with this characteristic that we put into this Rayleigh-Bénard convective flows. And we had the agent flying according to this law that if you sink, you can go horizontally, but you lose some height. And in the ensemble of turbulent flows, convective flows that I told you before, we asked the question that I told you previously, which are, what is the short-term sensorimotor cues that it's useful to sense in order to stay aloft. So the goal of the game is that there's an agent which has no engine, cannot flap the wings, there's no thrust, and it must navigate into this turbulent flow, which is made of ascending and descending currents. And the goal is to stay aloft, not to touch the ground for the longest possible time. Okay? So it's to stay up in the air for as long as possible without having any engine, without flapping the wings. And as usual, there's the usual problem of these policies of action, which is the problem of foreplanning and credit assignment. So if I want to train such an agent, it's clear that there's a problem of foreplanning, because if I make a move now, let's say, for example, I turn to the right or I turn to the left, this might have an impact in, say, a minute. I might gain some height at this time of seconds, but in a minute, because of this move, I may end up into a downdraft. So I must be careful with the planning of my actions, what they bring on the short term, but what they will bring also on the long term. And there's a problem of planning. And the second problem is the usual problem of training any policy of action, which is the problem of credit assignment. Imagine I start with a policy which is not, which an agent which is not trained at all. On the imagine I make some moves and I get to gain some height. It's hard to trace back in the whole history what was the good move that made that particular sequence of actions good. So there's the credit assignment problem. Now, in order to deal with this problem, we have not invented anything on this. We decided to take the usual standard framework for attacking this kind of problem, which is the framework that I've sketched here, which is the Q is the value, S is the are the states of the agent, possible states of the agent, and A are the actions that the agent can take. Now, I'm writing down the action, the equation for the action value dynamics, which is that the value of a given state and a given action at time t in a Markovian dynamics like the one that I sketched up there, where the agent can be in a certain number of states st, it's taking action a of t, and in response to the state and the action, it's getting some reward r of t. And this is repeated over time. The equation for the value over there is that it's going to get some short-term reward, and in response to the action a of t, it's going to transition from state s of t to the state s of t plus 1. There's a discount factor which is beta. Therefore, the discounted reward at the next step is going to take the beta because of the discount. And then it's going to have the value at the state s of t plus 1 and the action a of t plus 1 that you're going to take. So that's the recursive equation that is telling you what's the value of being in a given state and picking up a certain action. Now, if I knew that function q, then of course the best I can do in a given state S is to pick the action A such that I get the maximum value, and therefore the policy in each state S would be to take the action A that maximizes that value. And the reinforcement learning scheme, you don't have any model, you just learn empirically from the statistics, you train your system, you try to find out the Q by some scheme like SARSA, for example, which is what we used, and you try to learn this and to find out this policy which is here. Of course, you're all familiar with Sutton and Bartow book, the second edition, which is here, and there's a chapter, a paragraph where this application to soaring flight is being described. So what are the states in our case, and what are the action in our case? Well, the states S are what the flying vehicle can do is that it can control the angles. It can control, for example, the angle, the pitch of the plane. It can control the bank angle, which is how it's getting tilted this way. And of course, there's the state of the environment, which is the state of turbulence. These angles it can control, but of course this one it cannot control. It can infer where it is, if it's a good location or bad location, but the only thing it can do is that it can control this part here, and it can infer the state of the environment from the cues that it's receiving. So the actions A that the agent can take is to modify these angles, the bank angle and the angle of attack. So that's what the agent can control. Okay. Any question on all this? It's good? Okay. So, and then you use, in order to, of course, this is not an easy problem. I don't need to tell you in this audience that this is not an easy problem to learn. And in particular, what you can do is to use a TD scheme in order to update this function here. You start from a guess. You keep going, you do some actions that initially are pretty bad, and then you try to refine them by taking the difference between what is the left-hand side and what is the right-hand side. You pick the difference, which is here, and you correct your current estimate of Q with this estimated value, and eta, it's a learning parameter that you have to play with and to adjust. So in our case, what we do is that we take all the simulations of Rayleigh-Benard convection. Initially, we take an agent which is more or less changing angles in a random way, and over time, we update the value function. The value function here being the height of the agent after a few minutes that we decide, because usually this soaring flight of the birds lasts for a few minutes. We decide that to monitor the height at the beginning and the height at the end. So this is the value we are interested in. We update this function. And the policy that comes here, it's a soft policy where we take a temperature tau here. We cool the system over time. We start with a high temperature and then we cool it down. And we identify more and more greedily the action, the best actions out of this Q. That's what we do for the training. And this is what you get after the equivalent of 5 minutes training episodes, about 200 of them. This is what you get at the beginning of the training. So without any training, the agent is taking random moves, and no surprise, it's sinking like a stone because it's starting at 400 meters and it's going down over a few minutes, it's going down to less than 200. You keep doing the training that I've told you before, and this is what you get at the end of this 205 minutes episodes. You see that it's picking up this ascending current and it's spiraling up, gaining height in with some trajectories that are very similar to what you've seen before. So that seems to be working. I haven't told you exactly what the sensorimotor cues are. So let me tell you what the sensorimotor cues are. Here there's plenty of choices because the agent can sense many different things. But the most obvious ones could be temperature. Of course, I told you that you hit the ground, therefore temperature of the air close to the ground is higher than the other, than around. So temperature could be a good idea to measure, because if you pick up some hot air, probably this is a good indicator. In fact, it turns out that it's not. Here, you see this is the learning in kilometers. So temperature is a very bad predictor of, and it's a very hard quantity to use in order to gain height. This is the vertical velocity. This is the acceleration in the vertical direction. This is the torque. So let me tell you what the torque is. Imagine you have your agent, which is like this. The torque is telling you what's the difference in the vertical velocity because the right wing, between the right wing and the left wing. So it's telling you whether there's more push up in the vertical direction on this side rather than on this side. And you can imagine that this is a very useful quantity because imagine your thermal is located over there. So imagine the vertical velocity is going to decrease from the core of the thermal. And therefore, what you expect while you're flying with the thermal on that side is that you will have more push on this side than on this side. And therefore, the torque will be higher, will be tilted in this direction. Yeah. Y-axis is the learning in kilometers, which means that you have an episode like the one that I've showed you before of 2 or 3 minutes, and you measure how much you gain at the end of the training over a few hundred episodes, how much you gain at the end of the training. Okay? So how much you can gain by this learning series by using this one as the sensorimotor variable, this one, this one, this one. These are individual quantities. Or by combining a few of them, like acceleration and torque, or acceleration, torque, and all this stuff that you see here, and so on. Okay? Now, again, you won't be surprised that this one is acceleration and torque, and it's the one we picked up. This one contains everything, and in fact, it turns out to be worse for reasons that have to do with the training. So it takes longer as you increase the states and you increase the actions. Of course, it takes longer to train. So you might end up with the few hundred episodes that you have not well trained your system, and therefore you end up having a worse performance, even though these two variables are included among all of them which are here. So the choice of the sensorimotor cues is kind of obvious, is this one. It's acceleration and torque. Okay? So what you've seen before is that the agent is measuring the vertical acceleration and is measuring the torque. These are the two sensorimotor cues that the agent is picking. And this is what I've told you right now. And let me show you now that, contrary to my expectation, because I was expecting that the problem, I would actually need a huge, yes, sure. This one? Yeah. Yes. Yes. All of them. So that's the advantage of the simulations. I think it was a good idea to start with the simulations, because had we done the experiments first, all this kind of stuff would have been very hard to do. Yes. So we tried, these four are tried individually. Then we tried the combination pair by pair. I mean, we didn't take, this one we discarded, okay? It's too bad to care about. Then, as you can see here, we tried all different combinations. And we tried also to have different actions, which means we tried regulating the angle of attack or regulating the bank angle. And by the end of all this exercise that took a few months, we ended up with the states being the acceleration and the torque, and the control angle just to control the bank angle and not the pitch. The pitch is not very important. It's important for the gliding, but it's not so important to control into a thermal. So it was very empirical. Yes, all this was very empirical. We tried all this, and we saw what would be the result. Yeah. I don't think I teach you anything by saying that it takes quite some time to train. Yes, it does. But the good news, in fact, is that you can discretize the problem. So at the very beginning, of course, we tried to do very complicated thing. We expected we would do some deep neural net or something that we had to do, and we started that way. But then we realized, as we were training the system, that it could actually be trained in a much simpler way. And the end result, it might be disappointing, but to me was very surprising but very good to see, is that you don't need any complicated states, you don't need continuous states, you don't need to have continuous parametrizations. You can actually discretize your variable, acceleration and torque, in just 3 values. So very negative, small, or positive. And so by the end of all this, you end up with 9 possible states, which is the 3 by 3 of the 2 that you have here. And then the bank angle, again, you don't need to have it continuous. We decided to have just a discretization, to have the glider being in a state of 0 angle, +5, +10, +15, or -5, -10, -15, and you change by 5 or 10 or 15 the states of this bank angle. So by the end of the training, the flying policy is that in response to a certain state of the 9, and in response to a given position of the bank angle, you have either to increase the bank angle or reduce the bank angle, or to stay as it is. And this is the flying policy that we have to learn. Okay? And this explains why it might be, certainly you've noticed that 200 looks like a relatively small number. The reason why it's 200 and it's not 2 million or 2 billions is that we ended up with the lookup table, and therefore it requires much, much less episodes to train than you would have if you were to take a big state. Since it works, there's no reason to complicate your life, as you can see. So that was I have to say I was surprised. I was not expecting this, but this turned out to be the case. Okay, now having done this, now you can go, oh my God. Now you can go in the field, and we did the experiments. So we took a glider like this. We went into the desert east of San Diego. There's desert, so there's no shortage of sun. And this is Jerome Wang sitting and looking at the glider over there, which is, the glider has no engine. It has a system of control over there, which controls the bank angle in response to the cues that it receives. The velocity of the air is controlled by a pitot tube. And I won't tell you the engineering of how we measure the torque, but we managed to measure the torque. And this is after some training in the desert. This is the kind of trajectory that you've seen after the training. Again, this is a spiral, and it's gaining height. And you can't see very well, but the glider is over there. So the training is working. It's staying in the air without engine for times that in the good sunny days can be like 45 minutes, 1 hour. Yeah. Yes. No, we had to learn it again. The reason is that what I told you before, the big advantage of doing the simulations first is that we know what quantities we should be picking up. Okay, that one, as Lorenzo was saying, you have to train all the combinations, all the other things. So the big advantage is that we went into the field with 2 quantities to measure, which is vertical acceleration and torque, but we retrained the whole system. The reason being that the Rayleigh-Benard convection is not the dynamics of the atmospheric boundary layer. In particular, the size of the ascending current, the width is not the same, the strength is not the same, so we had to retrain everything. Okay. But again, it takes a few hundred episodes. So we discovered with the simulation what were the cues, and that we could train all this with a lookup table. So that was absolutely instrumental, otherwise we couldn't have done. But we retrained, yes, we retrained. So this is what you've seen before, and this is the height as a function of time. And this is a typical trajectory. Again, it's going around, it's losing some height, and then it's picking up one thermal and getting at the end of a few minutes to gain like 400 meters. Yes? Sure. Yeah. You're sure. No, you're a good lawyer, but the good thing is that it worked. But you're quite right. Hadn't it worked, we should have got back, retrained something, looked at something, but we were, we were, put it this way, we were lucky or whatever, and it worked. Okay, so it's working like this. Now, I cannot exclude that there's some other quantity that is even more convenient to measure. This kind of stuff, you're right, we cannot exclude. Yes. Right, so that's a very good question. I didn't tell you the reward, and there was a reason. The first reward that we took was the vertical, so it's a local reward. So the most natural reward would be to take the vertical velocity, because you integrate the vertical velocity and you get the height. This quantity doesn't work well. In fact, you cannot train. And I think the reason it doesn't work well is that you might remember previously, this is a Markovian dynamics. So the underlying thing that you have is that it's a Markovian dynamics. Now, the velocity in turbulence is a quantity which is very long range correlated. So in the formulation of the Markovian model, the reward at each time step should be independent from the previous one. Velocity in turbulence is not at all like this. Velocity in turbulence has correlation times which are of the order of several minutes. Therefore, this is a very bad model that fits the Markovian. So a little bit out of desperation and a little bit like of some intuition, we decided to take one derivative of the velocity and to take the vertical acceleration. The vertical acceleration in turbulence is very short correlated. It's correlated over times of the order of less than a second in typical condition. So it gets much better to that. With the acceleration, it works very well. Okay? So to answer your question, the reward that we take is the vertical acceleration. And then we proved something which is relatively simple to prove, is that if you have an optimal policy with a given reward and you take derivatives of the reward, the value changes, but the optimal policy remains the same. Okay? So the answer, the reward is the vertical acceleration. Any other question? Okay. So, and these are a few more examples that I have here. Now, okay, let me finish. I won't tell you about the trails. I can tell you later if you want. So getting back to birds, that's where we stand. We have now a relatively good idea of what could be some quantities that the birds could sense. That makes relatively good sense, again, in a different way of the word, because the birds are able to sense, for example, the velocity of the air. And I just want to conclude by telling you what's the state of the art in the measurements of what the birds can do. There's several papers. Recent one, for example, that one is putting up what you see on the back of the eagle over there is that there's a pitot tube which is put right on the back. So we are at the stage where you can have an idea of what is the velocity while the animal is flying. And the other thing which is clear is that these animals, of course, they do this soaring. That's quite obvious from what you've seen before. And the other thing which is quite clear is that there's a clear learning. That's an interesting news for this audience. If you take juvenile birds and if you take adult birds, the performance of juvenile birds compared to the adults is very poor. Therefore, there's really some training. It's not something that they do just by as they get. There's some training. There's some learning that they have. And if you compare this one, so the efficiency measured by meter per second that they gain, this is the juveniles and this is the adults. The proportion of the time that they have to flap in juveniles is much higher than what they have in adults. And there's also a very clear evolutionary advantage because those juvenile that don't manage to do soaring flies properly, the survival rate is much reduced. So there's a clear importance in all this. And the idea on the follow-up of this project, even though it got a little bit stuck with the lockdown, but the idea would be to try and see whether some of the quantities that we identified and the policy that we identified for the optimal agent would have anything to do with what the birds are doing. And I think I ran out of time, so I won't tell you about the trailing birds. And these are, again, the people we've been working with, and that's all I have to say.
Questions?
Yeah, so I guess one question is, so I know nothing about birds, reinforcement learning, and control, so I'm in an optimal position to be very surprised by everything. But one thing I was wondering is, so what's our state of understanding how a bird flight? I mean, we do send airplane in the sky, and these are not trained. There is perfectly controlled system. And so, yeah, I wonder, so, because on the one hand, here you learn everything and you try to discover. On the other hand, you have airplanes.
Yes.
And there are airplanes with, that do glide.
Yeah.
They don't do soaring as far as I know, but they do glide.
Yeah.
So I'm wondering, between the fully, totally data-driven model-free, and let's like setting down and besides the input, figure out the Excel, transfer function or whatever it is. What's going on? I mean,
What's
is
going
there
on?
any
Yes.
hope?
Absolutely.
Because you did, nail it down to not so many quantities. So
Absolutely.
I'm wondering if another direction would be to try to figure out the equations of soaring.
Yeah. So if you go back to the beginning of the history of aviation, it's actually interesting what you pointed out, because the Wright brothers, they started by trying to engineer something which was much closer to the birds. So at the very beginning of the history of aviation, people were trying to mimic what the birds were doing. In fact, what the birds are doing is much more complicated than what the airplanes are doing. And the reason is that the wings of the airplanes are rigid, so they're much easier to control than controlling the flapping wings of the birds. Even when they're gliding, in fact, the wings of the birds are much more, there's some control, they change continuously this, and this is very hard to control and to figure out. So, yes, the planes is much more a problem of control, and the birds is much more a problem of learning. Now, what is happening now along the way is that people are indeed trying to go in this direction. This is one effort, and there's more. One other problem which is that you might find interesting is that the people are trying to engineer some small flying vehicles of the size, for example, of the insects. This is a problem which is extremely complicated fluid dynamically to control, because over there you have to flap your wings. So it's a problem where you have to figure out by empirically, again, how to do this, because if you try to attack this as a problem of control, it doesn't work. There's too many fluctuations, too many things. So it's an open area where people are there's a very active area of research at the moment on this. Yes. But you picked up exactly the absolutely control and learning. And in the middle, the people are trying to balance, to put the two, and to try to figure out what to do. Yes.
Other questions? I have a small curiosity. How do you decide the time, the training time? So how do you decide to stop when it is learned?
We just decided on the basis of what is seen. You've seen the falcon at the very beginning. Typically, the time that it takes for a bird to take a height of the order of 1 kilometer is of the order of a few minutes. So we decided to take that time as the typical time of an episode. Is that okay? So maybe so the time that we take is 200 episodes of 5 minutes each. And each the 5 minutes, so I was answering 200 episodes is what comes out of the simulations. I mean, had we discovered that it took 2 millions, we would have done 2 millions. But of course, the experiment would have been impossible, because 2 millions in the field, it's impossible. Already it took like 2 or 3 months in the field to train. The 5 minutes, I was answering the 5 minutes. The 5 minutes is the typical time that the bird take to go from the ground to order 1 kilometer. So that's the 5 minutes. And 200 is just coming out of the dynamics. Of course, if you want to train something much more sophisticated than this 200 becomes much, much longer, no surprise. So 200 is for the lookup table that we yes.
I was wondering if the training is stable also for other like weather or soil conditions. Because
So in fact, that's a very good point, because in the field, of course, you don't control your conditions. What you do is that you cannot do all the episodes in a single day. Just multiply the numbers, and I told you that you have to be in the time of the day where the ground is heated up. So if you make a few numbers, you will find out immediately that you cannot do hundreds of episodes in a single day. You have to have them over several days. And several days, it means that the next day that you go in the desert, you won't find the same conditions. Therefore, what you've seen in the training is a fortiori robust, because we cannot keep the same conditions. Your question applies absolutely to the case of the simulations. In the simulation, we kept the same conditions, but empirically, it turns out to be robust, because in the field we couldn't maintain the same conditions over days. So the empirical answer is yes, it is robust, and also quite substantially, because it doesn't change just over days, it also changes over a single day. So yes, it is robust.
Other questions? I had a question about the migrations.
Yes.
So as the birds migrate essentially over continents, I was wondering, because the stability of the atmosphere will vary a lot, and in some cases there might not really be good times of the day, just because there won't be any thermals in the north, or I was wondering if the behavior of the birds changes. Is there any planning about when do you engage in?
Yeah. So of course, the number of thermals that you have when you're flying up in Canada is not the same as you're flying in the intermediate region over there. The remark that you can read in this book, I don't think they've done a plot like you would like to see, how many soaring flights they've done as a function of this and that. I've never seen any such plot. But what has been observed is been measured just by LiDAR measure. What is at the given time of the day, what is the density estimated this way? What is the density of thermals along these routes? And what is the density of thermals around regions where the birds don't migrate? And they found a statistically significant difference in increase of thermals along the routes. So clearly they've been selecting, probably evolutionary. I mean, they haven't studied the book and the Moni-Niaglom and found out where it would be good to fly. But evolutionary, they've been selected to fly along that route, and there's a statistically significant difference in the thermals, in the density of thermals along that routes. And of course, they're more concentrated in the regions where along the equator and the tropics than in the upper part. The other thing I told you about the time of the day, but ascending currents are generated by the thermals, as I told you, but it's not the only source of ascending currents. I told you the ridge soaring, for example. The frigate birds are flying over the ocean, and the ocean doesn't get heated up. Therefore, there might be other ways that you have ascending currents. In particular, over the ocean, there's no way you can get thermal, because there's no, the conductivity of the water is low, therefore it doesn't heat up. So there are regions where you have ascending currents just because of the circulation of air in those regions. It has to do with the orography. So they exploit along the way all sorts of things. And probably in those regions up there, they might be using some orography or some other things to save on this, on the metabolic cost. Any other questions?
Other questions? If not,
Thank you.
let's thank the speaker.
Thank you.